It's great to see you here. This is not going to broadcast in here, but Mariel should be able to hear me from this. And Mariel, do you hear me?
Yes, I do.
Awesome. Okay.
Hi.
Hello. And maybe you can see us. So hi, everybody. Welcome to our talk today on Dancing with Myself, Interdisciplinary Machine Learning Methods for Choreography. I'm Lee Spector, Professor of Computer Science. Before I introduce our speaker, I'd like to say a few words about the Artificial Intelligence in the Liberal Arts initiative that is sponsoring this event. As many of you probably realize, AI technology is rapidly becoming pervasive, and it is playing an increasingly important role in nearly every facet of modern society. AI is already having significant impacts on science, on commerce, on politics, on medicine, on media, on the arts, and on issues connected to almost every facet of life in modern society. In addition, aside from its practical implications, AI raises fundamental questions about the nature of our own minds, what it means to be human, how we should treat one another, and how we should treat non-human minds, if there are such things. It presents tremendous new opportunities, but also new and potentially catastrophic dangers. So the premise of the Artificial Intelligence in the Liberal Arts Initiative is that students and faculty and staff in all disciplines should have ways to engage with these issues, to explore and use AI technology, and potentially to play a role in the future that this technology will have in human society. In addition to sponsoring events, we're aiming to provide accessible AI software and hardware, mentors who can work with students and faculty and staff across the disciplines to understand and make use of AI technology, an online forum for discussions, and other initiatives. You can find out more at liberal-arts.ai, and you can join a discussion of today's event at our forum, which is discourse, D-I-S-C-O-U-R-S-E, .liberal-arts.ai. There you will also find a curated feed of accessible AI-related news stories, tutorials on AI software, tools, and more. And I really want to thank my student assistants to the program who have been doing an awesome job creating the forum, creating a new website, and setting up today's event, and are doing really great stuff. So now I am very much excited to introduce Dr. Mariel Pettee. Mariel Pettee has a PhD in physics from Yale University and is a Chamberlain Postdoctoral Research Fellow at Lawrence Berkeley National Laboratory. Her research encompasses the development of custom machine learning techniques for high-energy particle physics, as well as astrophysics. She is particularly interested in creating generic techniques that have broad applicability across other areas of fundamental science and art. Since 2017, she has also led independent teams of researchers using machine learning to generate choreography based on 3D motion capture of her own movements. As a choreographer, director, and performer, she also uses theater and dance work to enrich, to research audience activation, duration, power, self-documentation, authenticity, fear, and playfulness. Most recently, she has worked with companies including, how do you say that? Kinetech Arts?
Kinetech,
Kinetech Arts, LeeSaar, Urban Bushwomen, Paul Taylor II, and the Bill T. Jones, Arnie Zane Company. She was a choreographer in residence at Harvard University's Dance Center in 2014. Prior to her PhD, she earned her bachelor's in physics and mathematics from Harvard University and her master's in physics at the University of Cambridge Trinity College as a Harvard Cambridge Scholar. With that, I will turn things over to Dr. Pettee, who will give a presentation to be followed by a bit of time for questions and answers. Thank you so much. Mariel, please take it away.
Thank you so much, Lee. That was a really kind introduction. It's so great to see the crowd, right? I mean, it's been so long since I've given a talk in front of humans and live humans, and so it's just great to see your faces. So I love having that set up. Thank you for taking the time to do it. Love seeing the bubble tea too. I wish I could be enjoying that also. All right. So I'm sharing my slides. If they're not coming through, someone can let me know. So hi, everyone. My name's Mariel, and I'm a physicist and a scientist and a performing artist. And I'm so happy to get this chance to share with you some of the research that I've been pursuing for the past couple of years. So as part of a way of introduction, the kind of physics that I'm grounded in is in particle physics, and in particular, high energy particle physics. So the experiment that I've been affiliated with for my PhD and for the past basically decade has been the ATLAS experiment, which is at a facility called CERN based in Europe. So this is the largest particle collider ever built. And arguably, it's one of the largest and most complex machines that humans have built in human history. So it's part of this massive facility that stretches, it actually crosses between multiple countries, between France and Switzerland. And the detector that we use to analyze fundamental particles is about 6 stories tall. So maybe you can see from these slides, there's little people just shown for scale here. So this is my particle physics work, and this is where I spend a lot of my time. And as Lee mentioned, I'm currently based in California, out in Berkeley, and I'm working on machine learning for fundamental physics out here. And this is intentionally kind of a broad division where we are thinking about how to use machine learning for interdisciplinary work. In this case, specifically for fundamental physics. So that includes particle physics and astrophysics. But today I'm talking to you in a slightly different capacity, which is more along the intersection of my technical machine learning work and my love for and interest in the performing arts. So this has been part of a long time interest of mine of understanding how art and science can fit together in a way that feels organic and mutually beneficial and mutually respectful. And so one way that I've approached that over the past few years is to use motion capture to collect data of how I dance, and then to use my scientific background to help inform how I analyze myself dancing and how I can use science to understand more about my own artistic pursuits. So to be totally concrete, today's talk is going to be focused on this intersection between machine learning and choreography. So I wanted to mention at the top of this talk that this is a niche topic, and maybe it could be dangerous to suggest that I'm the only person who has thought about using technology in the context of dance. And maybe some of you in the room have a dance background. I'd love to hear more, but that's certainly not the case. There's a really rich history, particularly in the kinds of dance that I've trained in, which is mostly kind of modern, postmodern, and contemporary dance, of using algorithms, equations, games of chance, even motion capture and more to generate our work. So I certainly don't see it as this new radical thing in the dance world to use technology as a co-creative tool. But instead, I'm hoping to sort of see this work as part of a long line of different choreographers who are interested in thinking about the intersection of technology in their dance, and have set an incredible standard of interesting work over the past few decades along that line. So I'd say that this quote, which is by one of my favorite choreographers, the late Pina Bausch, really sums up my initial interest in this project, which is thinking about this very honestly common experience for anyone who's a creative type, which is that when you are trying to develop new work, or you're improvising or working in a studio, you sometimes find that you reach a creative rut. You find yourself doing kind of the same things over and over again. So I was really, I noticed this pattern about myself and in my own dance making. And I was using machine learning in my physics work. And I was mostly just curious to see if machine learning could help me generate new movements that were nevertheless authentic to my own dance practice. So that informs kind of the metrics that I had in mind when I launched this project back in 2017 for what success would look like in this marriage of machine learning and choreography. So I think there's a couple different bullet points that I had in mind. So there's this idea that I was curious to see if machine learning could create a realistic generated dance output. I wasn't even sure if that was possible. If that was possible, on top of that, I was hoping that it would also have this sense of authenticity. So it would actually seem like something that I would do as a dancer. And then on top of that, if I was able to achieve that, I was really hoping that the model would be able to surprise me and give me something that I hadn't normally thought to do in a dance studio. But sort of above all, I was hoping that this model would give me the desire to move and to dance. And that's why I've included this painting here on the left, which is by this guy, Henri Michaud. And these sketches that you can see, some of them, they're all figurative. They look like humans, but more so they kind of capture this like kinetic energy, this kinetic desire, and they make you feel like moving. So more so than realism, this idea that it inspires me to move was kind of the most important metric that I had in mind. So let me just sketch out sort of the previous work that existed at the time when I started this project in 2017. So in terms of thinking about folks who had thought about machine learning and dance, there were a couple different projects along these lines that had already existed. So on the left, you can see one example of some generated movements that were captured from what's called a Kinect camera, basically like an Xbox camera that was facing forward. And then on the right is the collaboration between Google Arts and Culture and the contemporary choreographer Wayne McGregor, where they extracted poses from video archives of his movements and created new dance movements in those same styles. So both of these models kind of used similar structures, and you can see they sort of captured a handful of points on the body. But one sort of problem with each of these approaches is that they had some difficulties capturing the full three-dimensional movements because they were either extracted from video or just from a camera that was facing forward. So we can contrast that with some of the quality of motion capture data that I was able to access at my PhD institution at Yale. So these are just some scattered examples of the kinds of input data that I was able to access, where now I have around 50 points on my body that I'm able to capture. And as you can see from all these different rotations, I was able to really get this three-dimensionality in the movement and really very smooth data throughout as well. So here's the setup that I used to capture my motion capture data. So it's basically a reflective suit with 53 points that are super shiny. So if you take a picture with flash, it looks like I'm glowing. And you can kind of see from this image on the bottom that there are about 20 different cameras that are simultaneously recording, and they're looking for these reflective points. So that's why I'm able to get such great three-dimensional quality from these outputs, and why why it's so smooth. There's a lot of redundancy in what these cameras are picking up. So the next couple parts of my talk, I'll basically I have two parts. So they capture these two different research projects that I led over the past few years. And they each of these projects dealt with two different independent research teams, where we were the first to apply the following machine learning architectures to the generation of choreography with motion capture data. So the first method that I will talk about is this method called variational autoencoders, or VAEs. And then the second method that I'll describe is graph neural networks, or GNNs. So starting out with the first one, variational autoencoders. So this project, it started off as this solo enterprise, and then over time, I started talking with more people, and I collected this amazing research team that was partially colleagues and collaborators at Yale. So that includes other physicists who worked with me and other machine learning specialists, folks from the digital humanities as well. And then also a couple of my friends from the dance world who think a lot about choreography and also the intersection of technology in their work. So together, we published this paper in the summer of 2019 that summarized our efforts in generating choreography with variational autoencoders. So for those who aren't familiar, I will just sketch out the basic idea of a variational autoencoder. There's two parts, right? There's variational and then there's autoencoder. So just the notion of an autoencoder is what I'll start with, which is that an autoencoder tries to generate outputs that closely replicate your inputs. So you can sort of see a cartoon of this here where you might input an image of a hand-drawn digit, and you actually want the output of the model to be very close and almost identical to what you put in. That might sound useless, but it actually, it has this great feature built in where you build in a sort of bottleneck into your architecture with a much lower dimensionality than your input image or your input data. And so the idea is that once the model is able to generate an image that closely reconstructs your input, that must mean that this middle dimension, this latent dimension, which is highly reduced, has learned a really efficient representation of your inputs. So it's an invertible, nonlinear, and very efficient form of dimensionality reduction for a data set. Moreover, the variational component of this means that we can use this autoencoder as a generative model. So rather than learning just a single vector to represent an input, instead I learn a Gaussian distribution for each of these latent dimensions from which I can sample in order to construct new sequences. So just some more details about the architecture here. So the task of what this model is trying to learn is that it's compressing a fixed length sequence of 128 poses that corresponds to around 5 seconds of movement at a time into a latent space. And from there, I can then sample from that latent space in order to generate new movements of around 5 seconds long. So here's just some selected examples of what I see from this model if I just kind of randomly, naively sample from the latent space. So you can see that the kinds of movements that the model is able to generate are, I would say, are realistic. They look like a human. For the most part, I think they look authentic too. They look like something that I would have done in the studio. And, you know, they're somewhat surprising and interesting and intriguing. So I think that, you know, even just using the model in this very basic format, it achieved a lot of the goals that I was hoping to find. But one of the stories of one of the takeaways of my talk, I hope, is that research takes you in a lot of different directions. And so even though I got something that I was happy with at this point, there were a lot of different ways that we ended up using this model. So next, I just want to show one example of this, which is a video piece that I constructed entirely out of generated movements. And in particular, what I was thinking about when I generated this video is to not take kind of the typical movements, which is more what you're seeing on this slide, but instead really trying to find the most unusual movements that the model could generate. And so I was really sampling from the far edges of the distribution and basically trying to break the model and seeing how far I could push it. So I'll show you a few seconds from that. I don't have a ton of time, so I can't dwell too long on those videos. But so that was kind of one immediate use case of this model, was generating new movements. And I'm also, since I'm a performing artist, I'm of course interested in translating these generated outputs back onto human bodies. So very early on in this process, we had a work in progress performance where at this point, this was like an early phase where I was only generating one point on my body at a time. So you can kind of see in this back photo, there's only one dot that's on the screen, and that represents my torso. So I was just trying to see if the model could generate a trajectory of how my torso was moving while I was dancing. And so I brought myself and a couple other dancers on stage. And so we were improvising on stage based on where the model was projecting our torso to move in space. So this was one early version of that. We also, later I got to work with my colleague and friend, Raymond, who's a beautiful mover. And that's a video that I'll show next. So this is a different kind of work in progress performance where he was actually able to get live feedback from the machine learning model while he was moving. So here's what that looks like. There's a couple different outputs that are being generated on the screen. You can see that he's actually wearing the motion capture suit, which is why the model is able to get live inputs of how his body is moving in time. And you can see sort of what the cameras are seeing, but you can also get a sense of where in the latent space of this variational autoencoder his movements lie. And that's what you see on this far left portion of the screen. So what Raymond is playing with is trying to explore as much of this abstract latent space with his movements as he's able to, because the model gives him some sense of, is he kind of staying in one place? Is he sort of playing with the same themes, or is he changing his kinds of movements very radically? So this was really fun to play with, trying to extract some meaningful information from the model in a way that can actually modify his performance while he is live. So next, I'd just like to share one of the other aspects of this model. So dealing with the same model, we realized that it had this other use case that I've found incredibly generative in my own work. And this is this idea of variations. So this exploits the idea that, that this model, once it has understood my movements pretty well, if I look at two different points that are fairly close together in the latent space of this model, those movements should be fairly related in terms of their kinematics. So this is a cartoon of what this looks like, but each of these generated movements are very close together in the latent space. And so you'll see what I mean. So for instance, these two movements, clearly they share a lot of features. A lot of my limbs are on the ground. My movements are very low to the ground. The timing is kind of similar. These two movements came from a different area of the latent space, but they seem to share something in terms of the timing of when I'm moving from a crouch to back to standing, and there's a little bit of a rotation in the same direction in each case. So you can see what I mean, that there's this kind of meaningful relationship in terms of the how close you are together in latent space for these different movements. And this is something I found some exciting ways to exploit as well. So in particular, it's this idea of taking a real sequence from my actual data set and then creating some variation on that original phrase. So almost like working in a studio with a different dancer, you're teaching them a movement and you ask them to just try something a little bit different. So what I'm showing here is an illustration of what that looks like. So here on the far left, in black is my real data, and in blue is the model's best representation of that data. And so you can see that the model is pretty well trained, because we see that the model has been able to capture pretty much all of the important kinematics of this original phrase. Now, instead, if I decide to not, rather than decoding the actual point in the latent space representing this phrase, instead, if I add a little bit of noise to that point, so basically I just look at one of its neighbors or just move a little bit further away from that original point and decode that new movement, then I get a movement that's very highly related to the original sequence, but is different in some way. So that's what you see here. I've added a little bit of difference, and the movement looks basically the same, except now there's this rotation at the very last step in the movement. And then if I move even further away from that original point in the latent space, then I start to get a movement that's even more different. And yet, as you can see, it still has this kind of significant correlation with the original phrase, and it seems to capture a lot of the same, to me, choreographic intent. So it was using this idea that early in the pandemic, I made this generated duet with myself. So next, I'd like to show you an excerpt from that. And it follows the same color scheme here, where the black represents my real data, whereas the blue represents this kind of generated counterpoint that is responding to each of the movements that I'm making over time. that's probably all I have time to show. So that kind of concludes that section on the variational autoencoder, and hopefully I was able to sketch out some of the many different ways that I was able to use the exact same trained model in my creative practice. So next, for the second part of my talk, I'd like to share a little bit about this extension of that previous work with a different model. So this was in the context of an internship that I did in the summer of 2020 with Intel's AI group. And I worked with these fabulous researchers who had backgrounds in deep learning in general, reinforcement learning, as well as graph neural networks. And together we were chatting about how I wanted to extend this work that I had just shown you. And something that kept coming up is that the model really has no idea that it's looking at a body, that there's any kind of structure to the data that I'm giving it. It really just sees it as kind of like a flat vector of inputs. So I was really curious to see what would happen if we used kind of a more natural representation of my actual movement data by giving the model some clues that it's seeing this kind of structure where there are relationships between these different points. And I was curious to see what the model would notice about this kind of structure. So this is where we came to the idea of using a graph, where basically we shifted the machine learning architecture to better suit the structure of my data, and still using this variational autoencoder idea, but now it has this kind of graph-based foundation. And just to define what I mean by a graph here, a graph is kind of like this illustration on the right, where a graph is a collection of nodes or points, and then edges, which represents relationships between those points. And the way that you train a graph neural network is basically you have features that are associated with each of these points and with each of these edges. And you can update those node and edge features by aggregating information from their neighborhoods. And if you sort of do this aggregation over a number of steps, then you end up kind of propagating information from the graph across the whole graph. So the model that I ended up designing is highly inspired by this project called NRI, or Neural Relational Inference. And the core concept here is that we want to learn a latent interaction graph to describe a dynamical system of interacting particles. So that's really well captured by this diagram here. So in this case, just in general, maybe you have some points that are moving in space. Some of them have relationships, maybe some of them don't have any relationship, but you don't necessarily know what those relationships are, and you want to understand what they are. So you want the output of your model to be an interaction graph. So you want, a point representing each of the points that are moving around. And then you want to have some sense of what the relationships are between each of those, including maybe there's no relationship between a few, and that's what's represented by these dotted lines here. So each pairwise interaction here is assigned one of some finite number of edge types by this model, and that includes no edge as an edge type. So this is just a sketch of what that looks like. So I'm using the same input data that I've shown you all before. So it's this collection of points that are moving in space, except now as an extra pre-processing step, I feed this data into my model as a fully connected input graph. So it sees every single pairwise relationship that's present in my body. Now I feed it into, just like what I'd shown you before, there's this kind of encoder and decoder as part of the overall autoencoder, except each of these steps are now graph-based. And now instead of getting the kind of latent representation that I was describing before, the latent representation here is for each of the connections, so for each of the edges, the model gives a prediction for which category of edge that relationship belongs to. And so it gives me a probability distribution of, oh, this edge is more like edge type 1 or edge type 2 or edge type 0. I sample from those distributions in order to get a single label for each of those different edges. And then I use that hypothesis of these different edges to then feed into the decoder. The decoder then predicts the future dynamics of my body, of the system. So let me just show a concrete example of what these edge types actually mean. So these are examples of the kinds of patterns in the relationships that this model has picked up on. And I should say too that I included a prior distribution on these edges. So I've asked the model to categorize 90% of the connections in my body as no interaction. So I wanted to really like ignore most of the connections in my body and to really only focus on a handful of meaningful edges. And so those handful of meaningful edges are distributed between 1, 2, and 3, whereas edge type 0 here represents the majority of the edges in my body, and they represent no interaction. And then what I've plotted here is the top 1%, sort of most representative edges that capture the dynamics of each of these edge types that the model has noticed. So you can see that this guy on the left, the collection of edges that it's identified, it's kind of a mix, and it's not really clear what the it's clear that it's just kind of a random collection of edges without a lot of cohesion. Whereas, for instance, edge type 2 here in blue, all of these most representative edges originate in my right hand, and then they stretch down to my left foot. So I feel like the model has really kind of picked up on what feels like this fundamental element of at least my ballet training, which is this notion of opposition of arms and legs. Whereas edge type 1 here, all of these edges originate from my left hand instead, and they connect to my upper torso. So the model has noticed this grouping of relationships that are all kind of similar between my left hand and how I carry my torso. So I found these to be just super interesting to get a sense of almost like an alien's perspective on what kinds of relationships the model is noticing. Since I unfortunately, I wish I could show you a performance that's come out of this work, but really because of COVID, I have not had access to dancers or dance studios for a little while. So instead, one way that I've played around with the outputs of this model is basically on a TikTok account, and also just playing around on my own, thinking about the different relationships that the model has identified. So, so here on the left, what you're seeing is one of the most highly ranked relationships that the model has picked out. So one of the most important connections. And that connection is from the top of my head to my right wrist. So that relationship is what I'm playing with in my improvisation on the left. And I found this to be really fun and fluid and generative and playful. Then what you're seeing on the right is one of the lowest ranked relationships that the model identified, and that's between my left toe and my left knee. And I mean, as you can imagine, it's just really hard to play around with that relationship. There's a bone in between those 2 points, and it's hard to vary it. So I kind of generalized it a bit, and I thought about it as the relationship between my feet and my knees. But I really found it to be like totally uncomfortable and weird to be playing around with this relationship that I truly never think about. So anecdotally, in this sense too, I think the model has picked up on something that feels true about which relationships feel important in initiating my movements, and then which connections I really don't think about anymore. So it's been cool to use it to get out of my typical methods of improvisation here too. Right, just checking the time. So yeah, I have just a couple minutes left. So let me just move on to some conclusions about this project, and then I'm curious to have a bit of a conversation if we can. So in terms of what I've learned about this project, so I've sketched out a bunch of different examples of different ways that I've used a lot of these same models. So when I started this project, I really thought it was going to have a single outcome, which was use machine learning to generate choreography. And I think I didn't anticipate all of these subtle different ways that I would end up using some of the same models. So I moved kind of beyond this sense of just generation and invention, more into this space of co-creation. So that's where you saw some of these variations on existing sequences, this sense of live feedback from the motion capture, a sense of expanding beyond my existing improvisational patterns. And even though I haven't used it in this way, I think it's interesting to think about how you might teach choreography in this kind of gamified structure where you're trying to kind of occupy the same space in the latent space in the way that you're moving, for instance. And I also wanted to mention that I've started thinking a lot about these models in the sense of creative preservation. I think a lot about documentation, and I really feel like there's not a great way of documenting my choreographic practice at this point in time. I have videos, but it always seems to, it doesn't really capture the sense of potential. It really just captures what I did on a particular day. So I found it to be pretty meaningful to think about this model as kind of preserving my choreographic practice with this body at this point in time that I can kind of continue to innovate with potentially forever. And though I haven't made steps in this direction yet, I find it interesting to think about how we could maybe use a structure like this to think about preserving other choreographers' practices, or to what extent a model like this really feels like it can authentically capture someone's choreographic potential. I've also found that sourcing the data on my own has been this like incredibly crucial and vulnerable part of this process. And it's informed why I start to think about these trained models as these precious and almost living forms of creative documentation. I've also learned that, and this was surprising to me, that I thought that the most impressive parts of this project would be the most realistic, smooth, beautiful outputs. But I've also found that glitches are so amazing for this type of work. And I think sometimes, like good art, the best results really lie at the very fringes of the model's understanding of how the human body works. So I found that, undertrained, or the messier parts of these models can look amazing and hilarious and weird and shocking and surprising. So it's really fun to just appreciate these whole parts of the process in a way that you can't always with scientific research. Like the mistakes are okay here. So sometimes they can be funny, and sometimes they can also just be beautiful. So a lot of these kind of messy in-between steps I have found to be a really valuable part of this creative work. It's also made me think quite a lot about my relationship to the model as an art maker. And it's led me to construct this sort of set of axes that this is just kind of my personal take on how I've viewed my relationship to the model over time. And I think over the past few years, the project has spent time kind of in each of these different domains. So I hope to continue to sort of explore all of these different ways of working with a model. But the axes that I think about are, so on the y-axis, I think about who is making the creative decisions. Is it the model or is it me? And then on the x-axis, I think about the nature of the relationship with the model. Does the model feel like it's my friend, or does it feel like it's not my friend? And so that can range from, up here in this top quadrant, there's this sense that the model is just helping me by automating my art making and just generating something new. If I want to feel like I have a little bit more of the creative power, I can think of the model as still helping me, but helping me in the sense of generating tons of outputs. And then I'm really choosing the parts that I find interesting. And then I kind of piece something together out of those generated outputs. Then down here, still with me making the creative decision-making, but thinking of the model instead as kind of not my friend. It's been thinking about the model as this external eye, this external observer, and maybe even a critic who's giving me feedback about what it's seeing. And then up here, which I find mysterious to think about in some ways, is thinking about the model kind of having its own creative experience, thinking about it just being sort of disconnected from my own art making, and it's kind of in its own world, generating movements and making some creative decision making in whatever extent that it can. And I thought I'd end just by, I've shown a lot of different applications of this model in my creative work. And I just wanted to highlight too, that I see it as having repercussions for my scientific work as well. And that's one of the cool things about interdisciplinary work, right? Is there's this exchange back and forth. So I think about this a lot in particle physics, particularly autoencoders, and this idea that you can use autoencoders for generation in the way that I've presented already. So this image here, and particularly this one in the middle, shows the application of a variational autoencoder for the generation of particle simulations. It's also useful to think about autoencoders because they give you a sense of what movements are kind of more natural versus abnormal. And of course, that notion of normal versus abnormal is really helpful if you're trying to find new physics or find some new discovery. Also, graph neural networks are very popular right now in particle physics for thinking about track reconstruction or even categorizing full particle physics events. We can step back even further and think about this, particularly the last project that I just described, the graph neural network. This whole problem of learning a latent graph to describe this dynamical interacting system can be applied to a lot of different types of problems, ranging from physics simulations to even like sports analyses, like thinking about how different players on a field relate to one another. Of course, it has implications for social networks and identifying different communities and how they're relating to one another. Potentially, it even has applications in sort of evolutionary development and trying to understand relationships between different cells while an organism is developing. One of my favorite applications of this kind of idea is this work from a couple summers ago, where this team of researchers did something kind of similar to what I was describing. So learning this latent graph to describe a dynamical system, but they actually take it a step further and use symbolic regression to extract an equation to describe each of the dynamics that the model has identified. And so they do this to extract Hooke's law from a basic simulation of balls connected by springs. And then they can even extend this to basically create equations that describe the density of dark matter in a simulation. So I find all this really encouraging, just to think about the ways that we think about these problems in general have so many different applications, as long as you can present it to the right person who can connect some of this generic work to some existing problem in their field. So with that, I think that's probably all I have time for. And I'd love to spend a few minutes taking any questions and getting your feedback. Thank you.
Thank you so much, Mariel. Can you hear me?
Yes.
Awesome. So the microphone is over. She's only going to be able to hear people who come down and talk to the microphone. But if people have questions, step right up.
Thank you for your talk. It was really interesting. I wanted to know about the applications of your research in the gaming industry, especially like virtual reality, because like the glitches in the dance moves kind of reminded me of the glitches in the game GTA. Like people just teleport from one place to another. And also like games in like virtual reality and like how we can like increase the accuracy of a computer actually like analyzing a human's movement.
Cool. Yeah, that's a great question. One of the Intel researchers who I worked with was really interested in these kinds of applications because I think, obviously it's such a large industry and animations in particular are really difficult to do. I remember him talking to me a lot about the idea of creating crowd scenes where you want the movements to look, natural and authentic, but you don't necessarily want to like hand program every single person in a crowd to be doing something. And so sometimes you end up with these like very artificial looking scenes where there are a bunch of copies of people doing the same thing. So I haven't spent any time, actually applying it in that domain. But I think you're right that I think there are some potential applications to creating, realistic crowd scenes in digital animation and in gaming.
That's right. Thank you.
Yes, I will switch off the screen share. Oh, yeah, there we go. Nope, I did the wrong thing.
Oh yeah.
Mariel, can you stop screen sharing? I think then
Oh.
we'll, there we go. Yes.
Hi, Mariel. My name is Jenna Beagle. I'm actually a professor of theater and dance here at Amherst College. So we have some dance students
Great.
here as well. So super exciting. It's fascinating work. Of course, coming from that perspective, I was curious about the choice to kind of avoid the central line of the spine as a point of multiplistic movement joints, and the ways that for me, I kind of understand our humanity so much through how much our spines and heads and tails move, like, of course. So I was curious, like, in seeing the kind of geometric lines that were formed in the data later on, in some ways that dehumanized it more for me than when I was just seeing kind of large pockets of dots moving. I could see the human form more. So I was curious, is that like a tool to help everyone kind of see a body or what we think of a body, or how did you come about that?
Thank you so much. I love that question.
Yeah.
Well, really, it was structured by the requirements of the motion capture facility that I was using. So they have these motion capture suits, but there's a very particular way of calibrating the dots on the body. And it's really oriented towards virtual reality and video game applications, people trying to make characters and then animate those characters. So that was one limitation. And I share your impulse, actually, and in particular, the Graph Neural Network project, where I was trying to find these relationships. Like, when I think about the relationships in my body while I dance, a lot of those relationships are in my core, in my torso. And then, I think about the initiation happening more centrally, and then maybe it ripples outwards. And instead, the model was picking up on all of these like extremity connections. And I found it almost embarrassing at first. I was like, I thought of myself as this one kind of dancer, and maybe it's just picking up on, I don't know, like only my ballet training or only this this other kind of movement. But it actually felt like the model didn't align with what I understood to be how my body was moving. So I think it's, I see it as a drawback of this motion capture system that I was using that had so many benefits, but it really was not collecting data from a lot of my torso and my spine and my neck. It was just focused on extremities because of the video game applications that it's using. So it's an interesting point. And I think as I continue to collect more data, it's interesting to think about what the model's missing.
Yeah, you could innovate other motion capture systems too.
Totally. I'd love that.
Thank you. It's really fascinating.
Other questions?
Hi, I'm Phoebe. I've been a dancer for a long time. So for me, dance and choreography is like very personal and very emotional. Like when I'm choreographing, it's a piece of me that I'm putting into like that dance, what I'm doing, and like that emotion that I'm putting into it. So how does being made by a machine interact with that? Like how do you embed that human aspect of choreography into the machine learning? And if you can't, how does that differ from other forms of dance?
Cool. Yeah, I'd say the model misses a lot of that. I mean, model misses in particular the sense of effort, sweat, muscle tension. There's like a lot of, and also I tend to emote a lot with my face when I dance. So I agree with you that there's really is a lot of data that the model is missing. One extension of this work that I've been working on with another PhD student is to actually annotate my data set with a sense of perceived effort, and to try to condition the generated outputs based on that sense of effort. So it's interesting to think about how to incorporate, maybe there's some sort of like force sensor that I could use, or other kinds of inputs that I could use to kind of augment the full texture of the model. I'd say that I think of my dancing, sometimes it's emotional. I think sometimes I think of it as it's playing with shapes, it's playing with timing, it's like solving puzzles. It feels contemplative and maybe not always emotive, but it varies. And I think what I really loved about the duet project that I showed you is that something that as a solo project just kind of felt like it didn't feel particularly emotional. It felt like I was just playing. Suddenly, when I had this counterpoint with this other body and this perceived relationship between those two, I started to see more of a relationship and more of an emotion come out in those ways. So, yeah, so I love the question. I think there's a lot that the model's missing out on, and I wonder, well, it's motivated this next phase of the project for me, which is thinking about adding in a sense of effort. And also I hope to extend this project to duets and partnerships. And I think that will bring more of that sense of relationship and emotion into the data too.
Awesome. Thank you so much. That's so cool.
Thanks.
I'm gonna sneak in a question. I've got two questions, but I'm gonna sneak in one. Very geeky one. I have students in a course I'm teaching on evolutionary computation, and symbolic regression is one of the things that we look at. So you applied the symbolic regression to the physics models. Have you tried it on the dance models?
I haven't, right. I haven't gone into the dynamics of the types of relationships that it's picked up on. But it's such a natural next step to understand.
Conceivably, you could derive the equations of your dance versus somebody else's dance by dance. Okay, I look forward to that. But we have another question.
Hi, I was wondering if you've considered combining the music with the choreography. So, like your first video showed, a dance where you put music to it. If you could put both the music and the dance moves into the same latent space, such that when you sample, you could give it either the music and generate the dance, or the dance and generate the music. If you've considered something like that.
Thank you. It's something I've thought about a number of times, and I think just in terms of the way that I make work, the music doesn't feel as central to the generation of the movement. So it hasn't felt that natural for me in my process, but I know of other researchers who are interested in this mapping between music and movement. So I think it's more that I think other folks are approaching that same question and they're doing it really well. And I feel like I'm more interested in other types of inputs in conditioning my particular movements.
Thank you.
Hi, I'm Alex. I'm an MFA candidate at Smith in the dance department, and Ilya says hello.
Oh, great.
Yes, and I was wondering if there is space to account for bias in the body, and how it seems like you really focused on you as a subject, and therefore your movement history and the archive of training that exists in you. And so I was wondering how, if at all, there's space to disrupt bias early on in this process, so that it's not necessarily something that you're trying to deal with later on in the process.
Could you say more? You mean bias in terms of me applying this model onto others?
Well, bias in terms of you, you seem to be working from a very specific definition of what choreography is and what dance is. And you are pretty clear in citing that that's coming from a predominantly white, predominantly balletic training background. And I'm curious if this model has space for more information than just that, and how, what steps could be taken now to create that space for the future.
Yeah, it's true that I really have primarily worked with myself as a research subject, and that's been pretty intentional. In some ways, I am hesitant to try to apply these types of models onto other bodies because I want that friction to be there where it's not so easily just like deployed on analyzing a bunch of people without their consent. So it's something I would like to do, is to bring in other types of movement backgrounds and movement styles into this type of work. But I guess I've just focused on, I really want to make sure that the data that I train on is like gathered fully consensually and, like with the total knowledge of how it's going to be used. So I felt fully free to kind of use myself as the lab rat in this case.
Hmm.
And
Also, you were in quarantine, right?
It's
like
true.
you were in quarantine,
Yeah,
so
I
you
was
had
limited
yourself,
in that sense
right?
too. Yeah, so I'm hesitant to, for instance, use to extract poses or movements from video archives of other dancers. I would really want to work with dancers myself and bring them into the studio with me and bring them into the practice. And that's what happened with Raymond, who really mostly has a balletic background as well. Yeah, so I'd say it's something I'm interested in. I both want to extend that practice to work very deeply with someone else of a different movement practice, but I don't want to make it too easy to apply this type of model for someone who might be a bad actor. So, I think it has to feel personal at the end of the day. I'd say that these models are pretty flexible though in the types of data that they can incorporate. And there's a lot that's missing in the types of movements and the types of data that it's collecting. So it's cool to imagine what other types of inputs we can include in these models as well.
Totally. Thank you.
Thank you.
We have time for maybe one last quick question if there is one.
I can go for one.
Okay.
Hello, can you hear me?
Yes.
Okay, this would be a silly question, but I was just wondering. So when you showed us the figure, like the black figure versus the blue figure, then the blue figure is the one that's the generated one, right? Not the real one.
Yes.
So I was just wondering, so as far as I know, like from looking through all the slides and stuff like that, when you add in the variations, I think we call that jittering. Correct me if I'm wrong, like introducing like random, noise into the data set. So the blue figure is basically just kind of replicating and copying your movements. So I think my question would be, what's the next step? Will there ever be a point where you'll have enough data set, you have a model that after that the program can decide for itself what the movements would be? So instead of like following your movements, it would just kind of dance on its own.
Yeah, right. My research team, initially, we played around a lot with trying to create kind of arbitrary length generated sequences, or I could say, give me a 2-minute sequence instead of 5 seconds at a time. And we actually just found that there were always discontinuities. We just had a lot of problems with creating something of an arbitrary length. So that's why we decided to stick with this kind of 5-second long movement. And then I can kind of artificially stitch them together to create long sequences. But I think you're right that it was kind of like just a natural limitation in our model, that this 5 seconds at a time. And I think with more compute and more training data, we would have been able to extend it to be able to generate even longer sequences. So I'd be curious to see what that looks like for sure.
Okay, thank you.
Awesome. Thank you so much. We're a few minutes over. I would just like to thank you one more time. Fabulous. Thank you so much. And thanks everybody for coming. And please go to liberal-arts.ai and click through to the forum, and you can ask more questions and have some interaction over this. I would love to get people's feedback and ideas for future events or other ideas related to what you heard tonight. Thanks so much.
Thanks all. Great to talk to you.